Okay, so there's going to be a little bit of coding in class if you want to set up a repository with the lecture 12 example code. The master branch is already kind of set to the beginning, and then there's a branch in that repository that kind of will have the finished product, so you can switch to the end if you after class. But during class, might as well play along, and there'll be some spots where I ask you to put together some stuff, and then we'll do it on together as well. All right. So today we're going to talk about sorting. And we're going to talk about sorting not because this is an algorithms class. You'll see sorting in much more detail in Comp 550 and talk about it more formally as an algorithm per se in some other class. But sorting is a nice example of big O analysis, right? So it'll demonstrate that, which we do care about a little bit here. It'll also give us an opportunity to define a new abstract data type and go through an axiomatic specification and basically have a practice with that, and we're going to also encounter a few things that are just kind of basic principles of both programming and thinking about programs and data structures, including the idea of invariance and divide and conquer, right? And in particular, this divide and conquer and this recursive kind of relationship between an algorithm, a recursive algorithm and its data structure is going to show up when we get onto our next big data structure, which is going to be trees, right? So wait, why does sorting matter, right? So it turns out that we rarely actually have to program a sort because, again, we're going to use libraries that already have sorting built in and it's done pretty efficiently, et cetera. Now, you might find yourself in a very specialized situation in which you care about sorting in a very, very specific context and therefore a more a handcrafted solution might be just the ticket. But for the most part, as programmers, when we need to sort something, we just kind of put it into a list and ask the list to sort itself. And it turns out list can, the list interface, the standard implementations of the list interface in java.util can in fact sort themselves, right? But sorting is a classic, is important to understand because it comes up so often. And because it comes up so often, understanding exactly the fundamental limits of how fast you can sort something and what it means to sort something given the specific implementation details of your data structure, right? And the implication for how long things are going to take, right? So in order to sort something, the very first thing we need to do is we need to be able to compare two things. And there is an interface in Java called comparable of type T, which essentially defines the idea that some type that you can compare, an object can compare itself to some other object of a particular type, right? It is one of the simplest interfaces there is. Basically, you can claim to be comparable in some type T if you can implement this particular method. Compared to, you give me something that is type T, and I'm going to come back with one of three values. -1 if this is less than whatever you gave me, other. 0 if we're the same, and 1 if we're larger. And that's basically, like what that means, of course, is going to depend on the specific data structure that says they are comparable in type T, right? So for rational numbers, that might be, you might have a data structure that represents a rational number. That might be one thing. And for strings, it might mean lexicographic order. For other things, the actual details for what it means to compare is going to depend on the semantics of the object underneath it, right? But it turns out that the standard implementations for list in Java basically provide a sort method that says, look, if everything in the list is comparable to some to each other, right? If they have if they implement comparable in their type, then the list can sort itself and it'll do so efficiently, right? So let's start off what we're going to do is we're going to start off with lecture 12.example1, and we're going to try to create a we're going to create a kind of object that that has some sort of sense of being bigger or smaller, and then we'll try to use that object when we in a list and try to sort it, and then we'll see what it means to implement comparable. Okay. So, starting off, if we look at our lecture 12, example 1, right? Let's pretend we have, or imagine we have some object or some kind of object that implements person, right? So person is going to be, this is an abstract data type, if you will. It's some kind of object that provides this operation. Now this, it's a pretty simple interface. We're going to think of a person as anything that has a name, right? And can retrieve its name, and can retrieve 4 numbers: fame, love, happiness, fame, love, and money, right? And those three numbers are going to be between 0 and 1, representing how much fame, money, and love that particular person has, right? Where 0 means you have none of it, 1 means you have, all of it in the world, right? And then we're also going to have this last property of this kind of object called getHappiness, and getHappiness is some function of the other 3 numbers, right? So, and different people might have different functions for what makes them happy, and so that's going to be our interface, right? So that's an interface that we're going to define, and now we're going to define a specific implementation of that interface, and that's going to be random person, right? So here is a random person class, and it implements person, right? So this is a concrete class that implements an abstract data type. What's the abstract data type? Person. How's the abstract data type defined? By its, what it can do. What can that particular person, what can a person do? Well, it can retrieve a name and retrieve 3 values for fame, love, and money, and retrieve some value for happiness between 0 and 1. Now, all of these, restrictions about between 0 and 1, I am describing to you. Presumably, if I cared to, if that's what the definition of the abstract data type would be, then I would put that into the documentation for person, right? Now, person is a pretty simple abstract data type. Basically, it's a simple immutable object, right? It just is 3 values and a name, and and some function that combines those 3 values to turn it into another value between 0 and 1. And so, we could do an axiomatic specification of this very simple data type, but it'd be kind of dumb because it doesn't really do anything, right? It's just a simple object, right? But right, given that we have this data type, person, we can provide an implementation. This particular implementation does so by having a name and fame, love, and money. And while this is not part of the abstract data type, this is not required of the data type as a whole. This particular implementation is going to, this particular concrete example of that abstract data type is going to combine money, love, and fame with some sort of factor, right? Fame factor, love factor, money factor. And when I create a random person, I'm going to use this static helper method to generate a name, and then I'm going to generate 3 random values between 0 and 1 as my fame, love, and money, because it's a random person, and 3 random factors for fame, love, and money, because, again, it's a random person. And then implementing the interface, I can retrieve the name, retrieve the fame, retrieve the love, retrieve the money, and then happiness is really just going to be this weighted average of fame, love, and money according to the fame factor, the love factor, and the money factor. And you can play around with this equation, but you should be able to prove, or kind of prove to yourself, that this is always going to give us some combination of those values that results in a value between 0 and 1. And if the fame factors are all, if the factors are all the same, it's basically an equal weighting. And if one factor is different from another factor, they're going to be unequally weighted by the proportion of their, of the factors, right? And again, that's just math, right? Okay. I'm going to override toString. What that means is, remember, every object really derives from this big object with a big O, and object with a big O in Java provides every object with certain built-in behaviors that every object has, and one of them is this idea of turning itself into a string. And so I'm going to override that so that I have a person, specific implementation, and that's going to be to combine the name and the happiness in some sort of string, and then be able to print it. In fact, I'm using just getName and getHappiness, right? And so these are interface methods, and since that I could, well, no, I'll just leave it here. So I'm going to override toString, right? Fine. So that way we can print out random people objects, and we'll get something reasonable, right? And then here's just my little helper function for generating a name. It just picks a random first name and a random last name from these two lists and combines them together, right? So this is a fairly simple kind of object, random person, that implements person. And now if we try to create a little program that creates an array list, and here I'm using the built-in Java list and array lists, right, the ones that are in util. And if I create a list of people, and now I basically create 10 random people and add them to my list, I can try to, I'm going to first comment these two things out. I can run this, and we should see it print out. Okay, here's my 10 random people, right? Barney Gachet, Fran Shaw, Abe Mayer, Barney Gachet again, Fran Cray, A.B. Mayer, et cetera, et cetera, et cetera. And then next to them are their happiness values, right? And we can see that the happiness values are in no random order. So it turns out that that built into list is the ability to sort the list. And so I could try to sort it and then print it again, but then I'm going to get an error. Right? And the error I'm going to get, the exception I'm going to get, is that method that sorts the list, right? The way you sort a list in Java is if the elements have a natural order, you can just call sort with the value null. And if they don't have a natural order, you have to provide an object that implements a comparison function, right? But the idea here is that the reason why this failed is because there is no natural order amongst people that I've defined, right? So we can define one. Let's define it by saying, oh, happiness, right? People who are less happy are smaller than people who are more happy. So if I want to to kind of express the idea that people are comparable to other people, then I need to essentially implement comparable in that type, right? So the first thing we're going to do is we're going to implement we're going to change our definition of person, right? So that person as an interface, right, also implements or extends, right, comparable to person. Okay? So the idea here is that comparable in a particular type is already defined in Java, right? And it basically says, it means you have a compare to method that returns -1, 0, or 1. So as soon as I do this, now I've defined my person interface is still there, but basically it says, look, a person has all these things, and right, it's comparable, right? So that it's right. So now when I do this, right, and I go to random person, it's going to give me an error. And the error is, hey, you said you implemented person, and person extends comparable person, and comparable requires a method that comparable in some specific type, and we said that person was comparable to other persons, and comparable as a interface requires this method, and this method is missing. So I'm going to give you guys just a few minutes to, if you have if you have Eclipse set up, great, try it there. If you don't, and your neighbor does, you can buddy up and kind of work it together. But go ahead and change the definition of person to be comparable, to extend comparable person as I've done. But then take a minute to implement random person, like to implement, right, to update random person to include the compare to method as required by comparable, right? Okay, so take a minute. All right, it's been a little bit. If you're still working on it, that's fine. Keep working on it. But if you think you have it, somebody, I'm going to say add unimplemented methods. And at the bottom, there's my compare to, right? Who wants to dictate code to me for the implementation of compare to? All right, come on, somebody did it, right? So we need to compare to some other person object. We said happiness is going to be how we compare if you are smaller than another object if your happiness is smaller. So how can I implement compare to here? Yes?
You take the function or the method of get happiness and then of the object is called on.
Okay, so give me an actual line of code here.
Smaller than other than negative, then return negative 1.
So smaller than other, like this? No. Dot get happiness, right? Presumably, this is other. I can rename that. Yes, that's right. Right. So then, if that's true, we're going to do what?
Return negative 1.
All right, and then otherwise.
Otherwise, you tell if get happiness is the same as other dot get happiness.
Like this?
Yeah.
All right, so. We're going to return 0. Okay, anything else?
Yeah, and then you and then you take the final one where you go else, and then if get happiness is I guess greater than other dot get happiness.
All right. Not bad. Okay. And this does work. Okay. Now there are a couple of things that we should, right? And this does work, right? So except that, what's wrong here? Because, right. It doesn't know that one of these things is going to be true. So we're just going to, here, we'll do this. If that's true and that's true, then we don't really need this, right? We know that if it's not less than and it's not equal to, then it's got to be greater than, right? That'll help us, hopefully. Oh, no. Must override, compare to. Oh, that's because I haven't saved this. Okay. Right. And that will work, right? Any way we could, any thoughts on this code? Any way we might improve it? So, yes.
Since get happiness returns a double, should we, are we allowed to use the double equals?
Right, okay, so that's a good point, right? So that is a point that we should discuss. I told you we shouldn't ever use double equals in order to compare two real values, and here we are doing that exactly, right? Now, here I'm going to contend, and you're right, if we had some definition of how close enough needs to be before we have the same happiness, then we shouldn't have this double equals. We should really have a subtraction of these two things, and then and an absolute value, and then a comparison of that absolute value against whatever that epsilon bound is, right? So if we did have some notion that that two people could be equally happy, and that we had some distance that we said is as good as 0, then that is correct, right? But this is actually, I'm going to contend, this isn't actually that bad, because even if two people are really, really close in happiness, if one is technically greater than the other, that's perfectly reasonable for one to be on, bigger than the other, right? And so actually I don't mind this double equals here, just because we could also say, oh, there is no notion of two things being so close that they might as well be the same. They either are the same or they're not the same. And if they're not the same, then one is bigger than the other, and we're only going to say 0 if in fact those two real numbers are exactly the same all the way down to the very, very last precision that real numbers can give us, right? So yes, that is something a good thing to have noticed, but in this particular case is not all that impactful, because we can demand that equality be exact all the way to the very, very, very last precision of the real number before we say these two values are the same, right? But okay, so there's no real logical problem with this code. Stylistically, however, this is fine, right? This is completely fine. And if this makes sense to you and that's how you want to do it, that's great. But stylistically, you start to learn that you can actually kind of say things that especially with the ternary operator, really lets you kind of say things kind of much more parsimoniously and a little bit more elegantly, especially in the case when you have this, well, if this is true, then it's this value, otherwise it's some other value, right? So if I wanted to rewrite this with the ternary operator, I could just say this. I could say return, and then ask the question, is get happiness less than the other get happiness? Question mark. If so, then return -1. Otherwise, and then here's another parentheses, do it again, is get happiness equal to get happiness? Well, I'm going to actually do the other one. That way it's just kind of easier. If get happiness is greater than get happiness, question mark. If so, then return 1, and if not, return 0. Right? So, I didn't expect you to come up with that one single line version of that same code. But as you kind of get used to writing, especially with ternary operators, you can actually kind of eliminate a lot of the verbiage with if, else, if if all you're doing is using that test to either produce one value or a different value. Anyway, so that's neither here nor there. Perfectly right? So now that we have a person as comparable to other people, if we go back to our example, our main, and try to do this again, it will work, right? Now we can create 10 random people and sort them and then print them again, and it works just fine. Because person is comparable to another person, the implementation of list didn't need to know what was in the list. It just needed to know that the objects that were in the list were comparable to their own type. And and in doing so, they're able to it's able to have a built-in generic sorting of the list, right? Okay. So the whole point of that exercise was just to introduce this notion of comparable to a type as an interface that an object can implement in order to kind of think about the idea of objects having a natural order. Okay. Well, okay, that's all well and good, right? Let's now think of a new kind of list, right? So let's go through our data structure design process with a new kind of data structure, which we're going to call sorted list, right? And a sorted list is going to be, a list that is sorted, right? Always sorted, okay? So a sorted list is going to be one where every time I add an element, it goes into the right place in the list, its natural order amongst all the other things, right? So remember what step one for defining a new data structure is, or a new abstract data type is the first thing we want to do is to have a functional specification that is that describes the operations on this abstract data type, right? So if we look at what we might want to do with a sorted list, right? It looks a lot like list, right? We have to have some way of creating a new one, right? And that's going to give us some sort of list, presumably an empty list, right? Now, we're not going to worry about the logic behind these operations. We're just going to describe them with words. So new is going to be some way of new, some sort of constructor that's going to give us a new list, some sort of insertion, right, where we take an existing list and we insert a new element and we get back a list, or it ends up in a resulting a list that is still sorted, right? Now note, this looks a lot like our functional specification for the list abstract data type, but in the list abstract data type, we said, we want to insert an element at a particular index I. That's not the way we can do this here. A sorted list doesn't let you just add an element at any place because it wouldn't necessarily be the right place for the element. You can add elements to the list, but it does not take a index. It just takes in the element, and there is a one and only way it can be inserted, right? Remove, right? I can still, given a list of a certain size, I can take some particular item, like some ith item, and remove it, right? So that looks exactly the same as it did for list. Get looks exactly the same as it did for list. I take a list and an index, presumably valid, and I get back the element at that index, right? Find. In list, we said, you can find an element, it'll give you back the index where that element was found, or some sort of indication of an exception. In most, like in some implementations, it might be -1, or it might, throw an exception or whatever. But those are the expected value is some index of where we found that element. Otherwise, some indication that we didn't find the element. This one's new. So this one we're going to add to our sorted list a lookup function that says you give me a list and an element that may or may not be in the list right now, but I will tell you what index it should go in or it would go in if it was in the list. In other words, right, I don't know if this element is there, but I'm going to compare it to the other elements in the list, and I will tell you where this element would belong if it did, if it were in this list, right? That's and so the value there is going to be anywhere from 0, it belongs at the beginning of the list, up to size, which is, it belongs at the end of the list. And then size obviously is the same as listed as before, and empty is the same as it was before, right? And so this is a very reasonable kind of specification functional specification of a sorted list abstract data type. So the next, so once we have our functional specification, right? Then it's time to specify some axioms, right? So remember the axioms, this is how we codify logically, this is how we reason about the correct operation of the data type, So the two steps to axiomatic specification was, one, identify which of the operations are canonical, which ones are absolutely required in order to be able to construct any possible version of the list, right? And which ones are not canonical. And then once we've decided which ones are canonical and which ones are not canonical, we need to combine them and then define their proper operation. But I forgot something, right? Actually, I gave away the answer, but now we can do it. So hold on, let me open up the Sakai quiz. There's going to be a Sakai quiz right now, as soon as I publish it. There it is. Okay, so the Sakai quiz is quiz the 2/18 quiz. It should be up there right now. And the one and only question is essentially which of these operations is canonical, right? So I'm going to go ahead and take a second to kind of get your little participation points for the day. Now, it's not that hard a quiz. Which operations that are required to create any possible version of a sorted list? It's the same ones that were required to create any possible versions of a list. And if you recall, the canonical operations for list were new, we need to be able to create a list, and add, right? Any possible list, we can just add, we can just create a new list and add each element in turn in order to create that list, right? Same thing for sorted list. We need new to be able to create one, and we need add in order to be able to add the elements to a sorted list. The nice thing about it is, like, it's even better than list. We don't even have to add the elements in a particular order, because we know that as long as we add all the same elements, a sorted list will end up being exactly the same no matter what order we add the elements in, right? All right. So once we have the two canonical operations, then we do the axiomatic specification by combining symbolically every non-canonical operation with the canonical operation and trying to construct an expression which transforms that operation into something we know is true, right? So these were the so some of these are pretty simple, doing this with new is usually pretty trivial, so we're not going to do that again. But these were the interesting ones for lists, right? Remember we said if the canonical operation insert, right, or add, right? I guess we use INS for insert. Inserting into list L element E at position I, that's the canonical operation, and then the non-canonical operation on top of that was removing some index J. The correct operation, right? We could reduce that combination into another small, like a different expression of that result. In the following way, depending on whether I was smaller or bigger than J, right? So if J is smaller than I, then for a regular list, it was removing something that we just from J, from position J, after having inserted something at position I for J smaller than I, was the same thing as removing the Jth item from L directly and then inserting the item at I-1 instead, right? And so we went from one construction of an operation, non-canonical operation onto a canonical operation into an expression of the same, where now we're dealing with the original list or a smaller list, or somehow we've made it kind of recursive, right? So now we can reapply and we know that the right-hand side is true if the left-hand side is true, right? Those two things are true if J is less than I. And then if J was greater than I, then we have a different thing that has to be true or can be tested as true. Another way of expressing that same result. And then if j is I, then obviously removing the jth item after inserting the jth item is going to be the original list, and so it reduces down to the original list, right? And so that was an axiom that made sense for list. So the idea here now is, can we do the same thing for sorted lists, right? So here is the sorted list, right? So these are all the same axioms, right? They're all the same combinations. But now let's think about what this means for sorted lists. Okay? So you'll notice that I've actually used lookup as a building block for one of my other axioms, right? So finding whether a list, if I find if I try to apply find onto the result of having inserted E1 into list L, and I'm looking for E1, then that's going to give me back the exact same value or same number as looking up where E1 belongs inside L, right? And same thing for the other version of find. If I'm trying to find something E2 onto the result of inserting E1 into L, it's the same thing as finding whether E2 is in L to begin with, right? If E1 and E2 don't equal each other, right? So the idea here now is, can we come up with something like these axioms for an unsorted list, but now for a sorted list, okay? All right, so okay, so if we're looking, right, if we ask for the value of looking up, actually, sorry, this needs a parameter. If we're looking up make this E1, make this E1, right? Actually, we need two versions of this one. Just like we did for find, right? The axioms for look are pretty simple. If we're looking for the position inside of the result of having inserted E1 into L, right? If that's our result list, and we're looking for where E1 is, it's the same thing as looking for where E1 ends up in L, right? And if E2 is not E1, then the same thing, right? It's still the looking up of E2, right? So, well, actually, no. So now now it depends on whether E2 is smaller than E1 or greater than E2, right? So if E2 is smaller than E1, it occurs before E1 in a sorted order, then this is the same, right? So if E2 is less than E1, right? Where we can compare E's, right? They're comparable things, right? And then otherwise, it's the same thing as looking up E2 minus 1 if E2 is greater than E1, right? So if I look in the original list for where E2 belongs and subtract 1, that will, actually add 1, then that will be the result of looking up E2 into the resulting list of having inserted E1 into L, right? So in this way, we can start to build up what we know is true about a sorted list, right? I'm going to skip to the actual answer in some sense, right? This first part with look is not right because I didn't do it correctly because I needed a parameter. But the other parts are pretty much the same. Right. So in particular, let's look at remove and get, right? Those were the interesting ones with the regular list, and we have the same interesting ones with the sorted list, right? And again, it's these axioms, these kinds of laws for what must be true afterwards, and what was, given that what was true before, right? That define the proper operation of an abstract data type in logic, right? So it basically says that if the list we have is the result of having inserted E into L, and then we try to remove the item at J, what is that? What does that turn into? Well, it depends. Was E, did E belong before J? Did it belong after J? Or did it belong exactly at J, right? If E belonged before J, then, removing J after inserting E into L is exactly the same as removing the J minus 1 item from the original list, because E would have slotted in before J, right? And then adding in E to that result, right? If where J belongs as where E belongs as after J, then inserting or removing the jth item after having inserted E into L is exactly the same as having removed the jth item from L first and then inserted E, right? Because the jth item would have been before E, and so the insertion of E or non-inserting E wouldn't have affected which item we're removing from the original list, right? And then if we're trying to remove the jth item and E belongs at the jth location, then if we insert E into L, that's going to be, because the lookup of E into the original list was J, that means that must be the jth item, and therefore removing the jth item will result in the original list again. We'll have undone exactly what we did, right? Now, these aren't the rules for just a regular list. These are only the rules that apply for a sorted list. There is an assumption that, right, there is, we've baked in the logic for what it means to be sorted by expressing it in these axioms. If these are true, then you are a sorted list because there's no way to be, to have these things be true and not be sorted, right? So one is the other, right? The axioms actually define what it means to be sorted. All right. Okay. So now let's actually try to. All right. So now we've kind of defined what our abstract data type is, sorted list, right? We know what the operations are. We've expressed the axioms. So that's all like kind of design work, right? We didn't write any Java code. We did this with just kind of using mathematical notation to give, to express the relationships of these operations on each other and what they mean, right? And so now, if we actually want to implement this in Java, we start by defining an interface that matches our abstract data type, right? Our abstract data type, except for the constructor. The constructor we leave for the class that implements it because it needs to know the implementation details. So other than new, all of these operations that are part of our abstract data type go into an interface in Java, right? That's how Java allows you to express an abstract data type, right? So the first thing we're going to do is we're going to write the interface, right? Sorted list. And now the idea here is that we're going to have the same problem that list did, that the original list that we used, java.util did, when we asked it to sort something that wasn't necessarily sortable. It threw a whole bunch of garbage and hit an exception. And the reason why is because it doesn't make sense to sort something that isn't comparable. If it's not comparable, then we don't know what's bigger and what's smaller. So we need to be able to express the idea that we are trying to write an interface for a sorted list on some sort of type, but it only makes sense for types that are comparable, right? So up to now, we've used these type placeholders to say, look, I don't know what type it is now, but when it gets used, it'll be told that this will, you will be given some type, right? Java also allows you to provide what's known as bounds, type bounds, basically to express limitations on the placeholder type. And one of the limitations you can express is you can insist that the placeholder type extends or implements a particular interface. And so in this case, right, if we wanted to create a sorted list interface that is applicable to types T, right, it only makes sense for types T that are also comparable to themselves, to other objects of their own type, right? So to write that, we use the following syntax, right? So here was our list of type T. We didn't care what T was, and then we defined our abstract data type as a whole bunch of methods, right, on our interface, some of which we were able to implement as default methods, some of which we would have to let a specific implementation fill in. Same idea. We're going to have sorted list, right? And we're going to have exactly the same thing, except now the problem is that it can't be just any type T. It has to be a type T that extends, that is comparable. So by adding this type bound, extends comparable of T, right, we are basically limiting the possible types that are used for T to just those that also implement, comparable in themselves, right? Okay, but if I do have, so in order to define this interface, essentially I want to do everything, right? I want to express as Java method declarations all of the things we said a sorted list should be able to do, right? So insert, we'll call that add, remove, get, find, look, what my size is, and whether I'm empty or not. In fact, it's so close to what we had already that I've already copied. We already did this exercise with list and array list a few lectures ago. So I'm going to go ahead and just copy this interface and change it as I need, right? So I'm just, to do that, I'm just going to copy everything inside here. Okay, I'm going to say, look, a sorted list is exactly like this list, right? Except, right, it's going to have a size, it's going to have an isEmpty, and that's going to, this default implementation is perfectly fine. Sure, I'll have a clear. Why not? I didn't really have that in the other one, but fine. Contains, well, I'm going to get rid of this one because just one less thing to have to write. Find, we need a find, right? And we can do it this way, but we'll come back to that later. We need to be able to add, but adding, right, does not just add to the end, right? Adding now needs to find the appropriate spot in the list and then add it there. So we can't have a default implementation for this. We are not allowed to add at a specific index, so I'm going to get rid of that. We can remove, right? We can remove a particular element by finding it first and then removing it, and then we can remove a particular element, a particular index. Great. We can retrieve a particular index. Again, don't have a default implementation for this because it depends on the details. And then we'll have set as well. I'm going to get rid of set just because it'll be one fewer thing to do, right? Great. And so that is my sorted list interface, right? And it has pretty much everything the list interface had. The only difference is that in terms of adding, I don't get to add anywhere I want. I can add an element, sure, but it ends up wherever it ends up, right? Okay. Right. Okay, so now we have to think, okay, if we're going to implement this sorted list, we know we have two possible strategies. We can either use an array, or we could use a linked list. And so we need to think about which strategy is going to make the most sense, right? Depending on how the list is going to work, right? Now, it turns out that the answer isn't really going to matter too much, right? Because it turns out the performance of a sorted list is going to be about the same no matter whether you use a linked list or an array list, right? And the reason why is because there's no adding at the beginning or end, right? There's no special, we can't use a sorted list for a stack or a queue because the elements don't get to decide where they go. The elements have to go wherever they go, right? Depending on their size and their relative size to the other elements in the list. So the key idea here is that the adding elements to a list, to a sorted list, is since you don't know where it's got to go, it could go at any point in the list. And if we know that if to add something to a random point in an array list is a order 1 operation, and to add something to a linked list is a order n operation, right? An array list is a constant time operation to add. Is a order n operation to add because wherever we add it, we have to push all of the other elements up the list, right? And so that was the knock on array list, was that if you add something at the beginning, you have to copy everything over. But with linked list, we could just add something at the beginning really easily. But here, we don't really have a choice about adding something at the beginning or adding something at the end. We may have to add at any random point, no matter what, depending on what element we're adding. So for an array list, it's an order n operation to add. For a linked list, it's an order n operation to add, right? Because we have to walk the chain until we get to the right spot and then put the element there. So either way, we either scan the array or find the spot in the array that we need to go to, or we walk the chain. It doesn't seem to really matter, right? For our sorted array list, and it doesn't, right? But just because we have to choose one in order to complete the example, let's choose to implement our sorted list as an array. Okay? So what we'll do is we'll start with the array list of T, right? And we'll just duplicate it and rename it and have it implement sorted array list. an array sorted list of T, right? And that's going to change, right? Our interface changed, so it's going to make some things wrong and some things right, and then we'll go through and we'll fix what's wrong and we'll make what's right. All right. So if you want to follow along, the first thing we're going to do is we're going to start with array list of T. We're going to duplicate it and rename it. Right? So I have my sorted list interface with all of my methods in it. And now I have my array list. That was the implementation of list. I'm going to copy it and paste it, and then say, oh, this is going to be my array sorted list. An array sorted list is not going to implement list. It's going to implement sorted list, right? And immediately we're going to see a problem, right? And the reason why is, well, look, sorted list only works with types T that are comparable with, in that type. And I have declared array sorted list to work with any type T. And I'm saying that, you give me any type, and I will give you back a sorted list of type T. That's not going to work because the interface says, no, this interface only works with things that are comparable. So just like I had to restrict what kinds of type I could use as T in my interface, I have to restrict what kinds of type I can use here in my class. So this only works for T, type T, that extends comparable in T. Okay, good. That's fine. But now the problem is that there are some things that I have that aren't that don't work, right? Size works the same. So how does my array sorted list work? Well, I have an array of elements and a size, an initial array size. This is all stuff I copied from list. So here's how I create a new array sorted list. No big deal. Size remains the same. Clear remains the same. Throw everything away. Add is different, right? This add is wrong. It shouldn't take an index. It should just take an element, right? Now, before we fix the code, right, because the code's going to have to change, right, let's start by looking at look, right? Look was the one thing that we didn't have, right, in our list. So let's start with that. Okay? So in our array sorted list, we need to implement look. Right? So, wait, hold on. Why does this not? This should have a red squirrely line because sorted list requires look. Let's try this again. All right. Oh, we didn't add look to sorted list. Right, okay, so, right, sorry. We need to add look to our sorted list, right? It's going to return a index. It says, okay, you give me the element, and I'll tell you where it ends up. Right? Now we don't have that, so we add unimplemented methods, and at the bottom it gives us so like, how are we going to do look, right? Turns out we can do look, right? If we look at find, like if we examine how a regular the original list did find, right? So go to sorted list and look and see how it did find. It scanned. It started at the beginning and went up to until it found the element, right? That still works, right? I mean, right? Like in this case here, it's finding the element, right? And we could take the same approach with look. We could start at the beginning and say, oh, is the element here smaller or bigger than the element I've been told to look up? And we could go until we finally found the spot where it belongs, right? But that would be not as efficient as it could be. And the reason why is because in a list, we have to start at the beginning and then scan all the way through the list because the things aren't in any particular order. But with sorted lists, we have knowledge about the structure inside the list that we can take advantage of, right? In particular, right? If we don't need to, the first thing we can do is we can say, oh, find is the same thing as we can first define find in terms of look. We can say, oh, well, first I'm going to look up the index where this element belongs. And then I'm going to get that element, right? And then if that element is the same compared to, right, the element I'm looking for, actually I'll say element, then I found the element in the list, right? Otherwise, I'm going to return -1. Oh. So in my sorted list, look and find are very similar. They take in an element and they either retrieve the index where that element really is found, or they retrieve the index where that element would have been. So because I know that look is going to have to be able to look up an element for where it would have been, I can rewrite find for my sorted list to say, hey, I'm first going to just look up where it should be, then retrieve that element, and then use the fact that these things are comparable to use the compare to method in order to decide whether or not I found it or not. But that still leaves me with look, right? Somehow I have to implement look. Now, we could implement look by starting at the beginning and going through, but that doesn't take advantage of the fact that we already have the list that's sorted. If you think about how you look something up in the dictionary, you don't start on the first page and then keep going, right? What do you do when you look up something in the dictionary? Somebody said something. Raise your hand if you know how to look something up in a dictionary. Come on. You have a huge dictionary, right? So if you have a huge dictionary and you don't have any lettered tabs and you just have some random word and you don't know, okay, so we have some understanding of the English knowledge, but basically what you can do is you just crack open the book to the middle and you think about, okay, and you look at the first word that's on that page and you say, oh, is my word before this word or after this word? If it's before this word, then you reduce your search to the beginning part of the book and you crack it open somewhere in that range and you say, is it before or after that point? And you basically make it so that you narrow down the spot on the page that you could be until, like a spot in the book that you could be, and then you find your word, right? And we can do the exact same thing for sorted lists. When we're looking for where an element belongs, we don't have to start at the beginning and scan, because we can just pick something in the middle and decide that, and see whether we would be before that in the list or after that in the list. And basically reduce the range of where the answer could be until finally we know where the answer is, right? Each time we've reduced the number of possibilities and by a factor of 2, right? We've chosen the middle, and either it's in the beginning or the end. And then once we know it's at the beginning or in the last part, we cut that in a factor of 2, and we cut that in a factor of 2. So where find by scanning from the beginning and going to the end is an order n operation, because we might have to go through the whole list. Looking up something in a sorted list is not an order n operation, because we are cutting down the range by a factor of 2 each time. And so we only have to do as many steps as necessary to narrow it down to the spot where it needs to be. How many steps is that? Well, this is the opposite of, if we divide by 2 each time, it's an exponential function, but instead of being, blowing up possibilities, we're dividing the possibilities by 2 each time. And so the opposite of an exponential, right, in terms of multiplying by 2 each time, is a logarithmic, right? So looking for the proper value by cutting the range in 2 each time is a log n operation. So we can look up a log n operation rather than an order n operation by relying on the nature of our sorted list and taking advantage of that in order to take a divide and conquer approach. Right? All right. So let's do that, right? So to look up an element, and I can do this entirely in the interface because I can do this as a default operation, right? I don't actually need to know how the list is being implemented yet, right? I start off with a low of 0 and a high of, the size of the list -1, right? So it's going to be somewhere in that range. And while those two things are not equal to each other, while low is less than high, right, as long as I have some range, I pick a spot in the middle, divide by 2. I get that middle element. And now I compare my element I'm looking for, or the spot for the element I'm looking for, with the middle element and decide, am I below it or above it, right? So if the element I have compared to, element I'm looking for compared, or the element I'm looking up compared to my middle element is less than 0, right? If it's okay, so the element I'm looking for is smaller than the element in the middle between low and high. So I know that the proper spot for my element has to be from the current low up to and possibly this middle spot. This could be the first element that is bigger than my element, and so this could be my spot, right? But it can't be greater. It can't be higher than the middle element because I already know I'm smaller. But I've reduced the range, right? The low is still the possible low, so low remains the same, but high is now can be set to middle. So I can reduce high down to where middle is. Otherwise, right, if the element compared to the middle element is greater than 0, right, if I know that, this element is bigger than this, than this middle element, right? Why is this not working? Yeah, middle. Oh, this is not int. This is type T. Right. Now, if the element I'm looking for is greater than the middle element, now I know that the element, the position for the element that I'm trying to look up has to be at least bigger than the middle's position, right? Can't be at middle's position because what's there is already smaller than me. It could be middle plus 1 and all the way up to high, but it can't be middle or lower, right? So now low can now be set to middle plus 1 because that's the low range, right? And high remains the same. And I keep doing this, else if, right? And then otherwise, right, if this happens to be, if the middle element happens to be exactly the element I'm looking for, then this index is in fact where the element would go, right? Now there's one little caveat. If I have lots of elements that are equal to each other, I want the index that is the very first index, right? So I'm going to go ahead and just return middle here, but in reality, this assumes that all of our elements are distinct, are different. But in reality, if we have elements that could possibly be the same, I could have a whole bunch of elements in my sorted list that all are the same, and I really should, not just return any random index in that, possibility. I really should return the very first index where this element, could go. So to make this truly bug-free, we would have to start at middle and march back down until we found the first element that wasn't the same, and that would be the index that we would choose. But I'm going to assume that all our elements are distinct and just return middle, right? We're going to keep doing this. Like if we get lucky, we'll find it right in at some point because middle will be the element, the spot we're looking for, right? But if that element's not in the list and we never, then eventually low and high are going to equal each other, and that's going to be the spot where this element should go. And when low and high equals each other, my while loop will end, and I can just return either one. It doesn't matter, low or high, and that will give me the right spot, right? This is called a binary search, right? It's binary because at every point we have one of two options. We're either above the middle or below the middle, right? Okay. Now we can actually go through and implement. We don't have to implement look anymore because we did it in the interface as a default method, but we still have to fix up add, okay? So add, we still have to fix up. Now, it turns out adding into a sorted list, right, is not all that hard. Just look up where the element goes, and then do what insert your element there, right? So this was what my add looked like in my original list, where I just added at a specific position index and moved everything. I don't have index passed in as a parameter anymore, but instead I can just look it up. I can just say, oh, well, look up where this is supposed to go, right? And I don't have to do this anymore because I know that I'll get a valid answer. It will either be, the appropriate thing, right? This is an array list, so I have to resize things if necessary. But then I just push everything over, and I put that element in the right spot. Okay? All right. And in fact, now we have a list that is always sorted. And if we go back to our original example way back here, and instead of using java.util, if we said, oh, let's use ours, lecture 12.sortedList, and basically say, this sorted list of persons is this array-based version of sorted list of person. Add a whole bunch of random people. Now we don't have a sort function because it should just already be sorted. Oh, we don't have a toString function either. So I would have to go in here and then override toString. Well, all right. Well, now at this point, I'm going to cheat, and I'm going to switch to the branch that already has everything done. Hello? I'm trying to discard the changes. Why are you not doing this? Fine. I will stash the changes. Git is killing me. Fine. I will just kill it and just start over. Not start over, but basically force it. Well, we're going to be running out of time anyway. All right, so right. Let's at least do the big O analysis here, right? It does work. Trust me, right? And but here, the idea here is that okay, if we try to use this data structure to insert, to basically create a list of however many items, n items. What's the big O analysis of inserting n items into my sorted list data structure, right? Well, if I'm doing something n times, right, then it's n times the big O analysis of whatever we did, right? So in big O analysis, you can, if you have a series of steps, the big O of the series is the same as the big O of any given step. If you have something that you repeated a certain number of times, the big O of having done it a certain number of times is whatever that number of times is times the big O of doing it once. In this case, I'm saying, look, I have some random, some value n. So however long the list is, how long did it take me to insert n items? Well, it's n times the big O analysis of how long it took me to insert one item. How long does it take me to insert one item in sorted list? If we look at what the add function does, it first does a lookup. We know that takes log n time, and then it does it does an insertion in the array and possibly moves everything over. And we know that takes order n times. So this is not a particularly efficient data structure because the total amount of time it takes to insert n items into my sorted list data structure is n times order n. Because every one of those insertions is an order n operation. The lookup part was fast. Sure, binary search made it that part log n, but the actual insertion was still order n because it was an array, right? And so we had to push everything over, right? And so our total time for inserting n items into our sorted list is n squared, right? That's not a particularly fast sort. Turns out that if we changed implementations and we used a linked list implementation, it wouldn't help us. Because sure, inserting a new element at a particular position in a linked list is an order 1 operation. We just have to unlink the chain and put in a new chain operation. But think about lookup. The reason why lookup was fast for an array was I could randomly pick the part in the middle and search for the subrange that contained the index I was looking for. And I could do that very efficiently in an array because randomly accessing into an array was an order 1 operation. For linked list, inserting is an order 1 operation, fine, but looking up, I can't randomly go in an array list, right, and a linked list. And so a linked list, trying to find the spot where the element goes, would have been an order n operation because we wouldn't have had any other choice but to start at the head and start, marching down the chain, right? So either way, either I did it with an array list, I still end up with order n squared for inserting n items into a sorted list, or I did it with the linked list, I would have ended up with order n squared inserting items with the linked list. So it turns out that sorting as you go along is not very efficient. It can be much more efficient to just insert everything at the end without maintaining the sort, and then sort at the very, very end all at once. And that's an algorithm we'll look at on Thursday. And then we'll start on trees.